So if you multiply CAB, like I said, see all this from here are zeros, and here I have just two non-zero elements, so it will give me again 0. So in order to get a non-zero thing, remember here I have r minus 1 zeros. The first element here is the rth element. So this 1 of B needs to move up, right, by multiplication by A, r minus 1 times to pass the r minus 1 zeros. So I'm going to keep doing that. So I need the 1 in B to move up via multiplication of A by A, r minus 1 times. And this will, to do that, I need r differentiation, right? So this is r differentiation. So the rth derivative is CARX plus CAR minus 1 B times U. And this is the first thing that I will get a non-zero. So this guy is actually the BM. So the BM will be multiplied by U1. In our language, this is the LGLF R minus 1 times H. Okay. So yes, the concept of relative degree carries over from linear systems theory. It's the difference between poles and zeros, but in other words, it's the number of differentiation of the output equation until the input appears. Okay? Any questions so far? Any question, please, about the concept of relative degree? So we call the system 1, we can do input-output linearization. Input, out. We can achieve our goal, and I showed you a little bit of how input-output linearization. If so, input-output linearization. Sorry, input-output linearizable. Here around, say, some x naught in M. It's input-output linearizable if it has a well-defined relative degree. Has relative degree, say, R at x naught. Then we can do the linearization. Let's have an example. This is, say, x1, say here, x3, x1, x3, cosine x3, 0, 1. Like I said before, the output is typically dictated upon you. It's the thing that you can measure, but let's assume that we have freedom to choose the output. I want to do linearization. We have x1, x2, x3. What about x1? If you choose x1, what would be the relative degree? If you choose your output to be x1, what would be the relative degree? Just 1, right? And 1, but not for all x. Luckily, cosine x3 around the origin, this is it's far from 0. So it has a well-defined relative degree around the origin, but not for all x, right? If we choose to be x3, what would be the relative degree? 1, and this time for all x, right? But actually a relative degree 1 is not a good thing, right? Because you will have just one equation linear, and the rest of the system is nonlinear. So we will choose it to be x2. So y dot is x2 dot, which is x3 plus 0u, so there is no u here. And now I'll differentiate again, so this is x3 dot, which is x1, x3 plus 1, right? 1 times u, so that's great, this is not 0 for all x. So I have relative degree 2, luckily. and I can choose my u to cancel this nonlinear dynamics. Right? In this case, I have my psi1 to be y, which is x2, my psi2 to be y dot, which is the x3. So the dynamics in these psi's is just psi2 and psi2 dot is v. I got you the linear part of the system. What about the nonlinear part? So like I said, this is a partial change of coordinates. I have x1, x2, x3. Now we go to psi1 and the psi2. This is the linear part. What is the remaining nonlinear part? Let's see. So psi1 is actually x2, psi2 is x3. So the remaining part is what? The remaining part is what? Is x1, right? So I will have here the x1 dynamics. So here is the x1 dynamics. I'll just write it again. This is x1 plus cosine x3 times u. Actually, x3 in my new language, this is psi2. And u, from the feedback law, this is negative x1 x3 plus v. Again, x3 is just psi2. So this is my entire transformation from x's to psi1, psi2, but I have one of these x's. This is purely linear, but this guy is nonlinear. There are two issues here that we need to address. Two issues with this red equation. The first is that the x1 dynamics, the remaining dynamics, depends on the input, depends on v. What's wrong with that? You will adjust your v here to achieve whatever you like, and indeed you will. But this v is here, so it may do crazy things for the x1. You don't want to do that, right? The issue, I will not be able to treat them as a whole. I could have done it from the beginning. I want to focus on my linear part. So if you do something for the linear part, this may ruin x1. So we need to just get rid of the dependence on x1. That's okay, because I transformed some x's to the psi's, and this guy didn't transform it. So now I can look for a transformation for x1 such that it's void of v or u. So this is easy to fix. I will look for phi, so from x's to phi of x, such that phi will be the third coordinate after psi, such that phi should be nu, so it should be independent of the psi's, and phi dynamics should be void of the input. So this is Lg phi should be 0. This means that phi dot is void of u or v. So let's do it together. Let's do Lg phi is 0. Please pay attention here. So this is your g, right? So let's do the Lg phi. What's the Lg phi? So the partial phi, partial all the x's dotted with this guy. So cosine x3 partial phi partial x1, 1 times partial phi partial x3. Cosine x3 partial phi partial x1 plus 1 partial phi partial x3. This is 0. Okay? What is an obvious solution for phi here? What is an obvious solution? Well, the 0 solution is okay. Well, what is a little bit less trivial than the 0 solution? What's obvious here? What is a function of x1, x2, x3 such that if you differentiate it like this, you get 0, obviously?
Phi function of x2.
Very good, x2. Any function of x2, let's say x2, so x2 satisfies it, right? So actually x2 is a solution, but what's the problem with that? What's the problem with that? Is that it's not a new coordinate. I have x2 already. x2 is my psi1, right? But x2 is psi1, so this is not independent. We need an independent solution. So we'll do it the usual way we do things. We solve these partial differential equations, the linear ones. How we do it? dx1 divided by the coefficient of derivative with respect to x1 equals gx3 divided by its coefficient, right? And phi is constant on this equation, on this surface. We'll do separation of variables, so dx1 is cosine x3 dx3, integrate, have a constant, so we have x1 equals sine x3, right, plus a constant. We can just move this guy here and have this guy equal constant and actually ignore the constant. So phi can be taken to be any smooth function of this argument. In particular, we can take phi to be just x1 minus sine x3, but you can take it whatever, e to the power this guy, sine this guy, cosine this guy squared, whatever, everything will work. So here is my phi. So now I solved the first issue. Why? Because if you differentiate phi dot, this is x1 dot minus cosine x3, x3 dot. x1 dot was whatever. x1 dot is this guy. x1 plus cosine x3u, this is x1 dot, minus cosine x3, x3 dot, which was x1, x3 plus u. And by construction, this guy should cancel. And indeed, you have the phi dynamics to be x1 multiplied 1 minus x3 cosine x3. In the new coordinates, x1 is just phi plus sine x3, and x3 is psi2, 1 minus psi2 cosine psi2. So this is in the new coordinates. So the summary of this, the final thing with this problem is we have, from the x's, we got psi1 dot is psi2, psi2 dot is just v, this is the linear part of the system, and here is the remaining dynamics. The phi dynamics is phi plus sine psi2, 1 minus psi2 cosine psi2. So we solved the first issue. There is a second issue, however. Any questions so far? Any questions so far? Okay, what is the second issue? The second issue is that the phi dynamics is completely unobservable by psi out. The phi dynamics, or even the x dynamics, it doesn't matter, x1 dynamics, the remaining dynamics in whatever form is unobservable from the output or any of the entire psi dynamics. What is the issue with that? Let's recall here our input to complete the picture. Remember, the input was negative x1, x3, so x1 here is phi plus sine psi2, x3, which is psi2 plus v. This was the input from above here. So this gives you everything. Let's see here. The phi dynamics does not affect any of the psi's. So there is no any phi here, right? There is no phi here. Which means if you adjust your input to achieve some desired response for psi's, you will perfectly get it, that's fine, and you will have no clue by measuring psi's only. You will have no clue what phi is doing. Phi may be blowing up, okay? That's okay if you care about psi only, which normally we don't. We should care about all the states of the system, but even though if you care about the psi's only, and I don't care about the phi, what will happen? Actually, you may even lose stability for psi's. Why? I mean, we said just phi doesn't affect the psi dynamics. That's right, but it typically affects your input. So you adjust here your input to achieve whatever you like here, and this is your actual input. So whatever you have plus this guy, this is your actual input, the motor speed, the valve opening or the elevator deflection, this is your actual input. So if the phi is blowing up, the actual input will be, the required actual input will be very large, so it will cause saturation in your system, saturation in the input, because any input is just limited by bounds. The elevator cannot move beyond 30 degrees and negative 30 degrees, right? So if you require here 60 degrees, what will happen? Well, the system will give you only 30 degrees, so input saturation, which means this V is not as desired. So actually you may even lose the ipsi stability, okay? So this is the issue, is that this dynamics is unobservable here, and it affects your input. So it's bad, affects your feedback. So we need to resolve this. We need to make sure at least if ipsi is going to 0, if I say I want to regulate the ipsi dynamics, or I have a trajectory and I want to track this trajectory, so the error of this trajectory, ipsi represents the error, so I want to drive it to 0. Okay. I want to drive ipsi to 0. What happened? Are we okay if we design V that makes ipsi 0 with this property, with this story that we had? Are we okay? Here we have a lemma. Two systems interconnected like ours exactly. So this is, say, the zeta dynamics is some function of zeta, and the origin is an equilibrium point. We have the eta dynamics is another function of both eta and zeta. And again, the origin here is also an equilibrium point. So first of all, do you see the matching? So the zeta dynamics here is the psi dynamics after you design your V by some state feedback and make it nice and everything is good. Now it evolves on its own. The zeta is the psi. The eta dynamics is depends on both eta and zeta, which is here phi depends on both phi and psi. Okay. And I want a result like